Do you have a portable mic or?
I think there are these two.
Oh, thanks. Yeah, that's great. Everything good? All right, so it's a pleasure to welcome Latham Boyle here from the Perimeter Institute, and he's going to tell us about the Penrose tiling, self-similar quasicrystals, and fundamental physics.
All right, so thank you very much for the invitation to speak in this interesting workshop, or program, I should say. Yeah, so I am, for those of you who don't know me, I'm maybe mainly a cosmologist by day, but I have a side interest, long-standing side interest in the Penrose tiling and other self-similar aperiodic tilings and crystals, and in particular, they have sort of a famous role that they already play in physics, which was awarded a Nobel Prize about a decade ago, which I'll review in a moment. But I think they turn up in two other places, which are kind of interesting possible alternative ways they could appear in fundamental physics. And so I kind of wanted to introduce you to them as both mathematical objects, and then also give you an idea about these two possible applications. Oh, so I should say, so I'll be talking about, the talk will basically have two parts corresponding to these two applications. The first part is based partly on a paper, Conformal Quasicrystals and Holography, which, let me highlight a little bit here. The first part here is based on this paper, Conformal Quasicrystals and Holography, that appeared 2 years ago in PRX. And that was with Madeline Dickens, who's a PhD student at Berkeley, and Felix Flicker, who's now a faculty member in Bristol in the UK. And then even more on work in progress with Justin Culp, who's on the call here and who's an excellent PhD student at the Perimeter Institute, who will be going on the job market this year, I believe, postdoc job market. And the second part is this application, space-time quasicrystals and the origin of 3+1 dimensions. That's work in progress with another outstanding PhD student at PI. He's just beginning his PhD now. That one is, I decided to talk about it because I think it's a fun topic, but that's really very much, this first topic is work in progress in the sense that we have the result and we're writing it up, and I hope we'll have a paper out about it in a month maybe. This second one is both more speculative and also more, let's say, undercooked, but I still think it's interesting, so I just wanted to say a little bit about it. Okay, so for starters, though, I just thought I would introduce you to the Penrose tiling and things like it, just to get the lay of the land. And so here, for starters, I thought it was just for fun. I originally, when I was planning the opening slide of the talk, I thought I recently got, they recently gave me access to DALL-E. I don't know if anyone has played with this new sort of artificial intelligence that can very impressively generate arbitrary images in response to an arbitrary verbal prompt. And so I thought I would give it the title of my talk, the Penrose tiling, self-similar quasicrystals in fundamental physics, and see what it generated. And I got these two kind of, I thought I was rather impressed by this. I thought I was ready to read rather deep things into this response. In particular, you notice the star on the left is actually a 10-pointed star, not the blue star in the middle there, which, as I'll mention in a moment, is seems like an impressive bit of understanding from DALL-E. But then anyway, and maybe it was, then I was a little disappointed. I next just gave it fundamental physics by itself as a prompt, and I got these 4 images, which anyway, so made me more dubious, but there you go. So good. So to introduce the idea of quasicrystals in the Penrose tiling, it's good to start with this famous theorem about ordinary crystals, ordinary repeating patterns, where by repeating patterns, I mean patterns with some translational symmetry. And so there's this famous theorem in crystallography that in 2 and 3 dimensions, 2 and 3 dimensional Euclidean space, that patterns with discrete translational symmetry can only have points of 2, 3, 4, or 6-fold symmetry. Other symmetries, points of 5-fold symmetry or 7-fold symmetry, for example, are not allowed. And so, here, just for later purposes, let's introduce a bit of notation. This is this Shapley notation for tilings and polyhedra. This tiling here, of course, the famous square tiling that you are familiar with from bathroom floors, would be denoted a 4-4 tiling, where the first 4 denotes that each cell in the tile, each tile is a square. And then the second 4 denotes that 4 of these come together at each vertex. So we have four squares coming together at a vertex. So this tiling is a 4-4. Here's another tiling here, a tiling, of course, also very familiar by hexagons. This would be a 6-3 tiling because each tile is a hexagon, a 6, and 3 of them come together at each vertex. Okay. Okay, and so you can see already in these 2 tilings all of the allowed points of symmetry. So at the center of every square here, or at the vertex where 4 squares meet, that's a point of 4-fold symmetry, 4-fold rotational symmetry. At the center of every edge is an example of a point of 2-fold rotational symmetry. And where 3 hexagons meet here is an example of 3-fold rotational symmetry, and at the center of every hexagon is an example of 6-fold rotational symmetry. Okay, and the theorem says that's all that is allowed, and let's see briefly why that is. There's this kind of simple argument for why that is. So, which I've tried to sketch here at the bottom, which is, so suppose we have some tiling, for example, that does have discrete translational symmetry, but also did have a point of 5-fold symmetry. Okay, so then, and the idea, when I say discrete translational symmetry, I guess what I mean by that is that it has points of 5-fold symmetry, but they're distributed like in a crystal. So there's a minimum distance between them. They're nearest. There are some nearest neighbors that are separated by some finite positive distance in the lattice. So let's imagine that these are 2 such nearest neighbor points of 5-fold symmetry. Well. But then if this guy is a point of 5-fold symmetry, this guy on the left, then if he sees a point of 5-fold symmetry off in this direction, he better also see a point of 5-fold symmetry at the same distance, an angle 2 pi over 5 away, because after all, he's a point of 5-fold symmetry. But then you can make the same argument sitting at the position of the guy on the bottom right, that if he sees another point of 5-fold symmetry this distance away, he'd better also see another point of 5-fold symmetry this distance away, and an angle of 2 pi over 5 away. But the problem is that now we've created 2 new points, which are even closer than the 2 points that we started with, which is a contradiction, because the starting assumption was that there are points of 5-fold symmetry with some minimum separation, and we had started with a pair with that minimum separation. Okay, and so anyway, so basically a similar argument holds for every symmetry, for every possible rotational order, except for these special cases 3, 4, 6, or 2. Or you can see for easy reasons that the argument fails. Okay, so then, which brings us to the Penrose tiling. So there was a question that some mathematicians were interested in the, I guess, the 1950s and 60s. A question of whether you could find tilings of the plane, where you cover the plane with tiles with no gaps or overlaps, but they only cover the plane in a way that has no translational symmetry. And some rather complicated examples had been come up with that satisfied this property, but then there was this famous discovery of this pattern, very beautiful pattern with only 2 tiles that did the trick. And this was discovered basically by thinking about the previous theorem. Basically, the idea was that if you could find a pattern that only tiled the plane with 5-fold order, that it would have to not be translationally, it would have to not have a translational symmetry by the previous theorem. And so you'd be done. And so Penrose, and independently this guy Amann, played around basically, well, it's unclear how Hamann discovered it, but Penrose, we know, played around by sort of just thinking about playing games with how you could start with a pentagon and decimate it into smaller and smaller shapes where you kept getting repeated copies of the same few tiles appearing, same finite number of tiles appearing. And anyway, they discovered this tiling, and in addition to having the desired property that it only tiled the plane in a way that had no translational symmetry, so it sort of continually goes on repeating itself, but never managing to quite repeat itself if you follow it far enough. It also, it turned out to have many other sort of beautiful and miraculous properties, and it became a topic of interest to mathematicians then in the late 70s. And there was a lot of interesting stuff figured out by mainly these four people. Hamann, who was not an academic, he was just an amateur mathematician who worked as a mail sorter in the post office. And then these three much more well-known mathematicians. Yeah, for a good introduction, you can't do better than Martin Gardner's original article about this in 1977, to the Penrose tiling, that is. And then for an introduction to this guy, Hamann, who is the one in this group who really figured out the most about this tiling and related tilings, and is the least known, I recommend this article by Marjorie Seneschal, The Mysterious Mr. Hamann. And actually, I'll just say one thing about him, which is that, so he never wrote a paper himself that he published. We know everything he did because he sent letters to Martin Gardner explaining what he did, what he had figured out. But he did, and he was apparently rather, unfortunately, he was rather reclusive and unfortunately died young. But Marjorie Seneschal in this article describes how she sort of made repeated attempts to meet with him, and one time succeeded. And the one time she did succeed in meeting with him, he did give her the one paper that he had written, which was a paper that he sent to Nature, which unfortunately, anyway, which was not published. So it was never published, but it was his proposed explanation for the extinction of the dinosaurs, which was different from the standard one. It was that it's a rather technical, it looks from a distance like a normal technical letter in Nature, but look a little bit closer. And basically he's arguing that he's giving all sorts of bits of evidence that the dinosaurs, that the most intelligent dinosaurs became rather intelligent so quickly that it didn't leave a discernible mark in the geological record, but then that they managed to blow themselves up in a nuclear extinction event, and in a nuclear war, basically. And anyway, suggesting various observational traces that would leave and ways to look for that. So as far as I know, that theory has not been, well, anyway, whatever. So anyway, he was an interesting and unusual person. That's what I mean to say. Okay, so now to the Penrose tiling. I want to give a quick introduction to the Penrose tiling just to set the stage here. So the Penrose tiling is built of two tiles. In this standard presentation, there's different ways to present it, but there's a sort of thinner rhombus here and a fatter rhombus. And one way to create the tiling is just to start with an initial seed of tiles, like for example, the set of 5 fat rhombuses. And then every time you see a red rhombus, you make this particular, you decimate it into smaller red and blue rhombi as follows. And every time you see a blue rhombus, you decimate it as follows. And so if you just start with this seed, for example, you can start with whatever seed you want, but then you substitute, and then you substitute again. At each step, you get a bigger and bigger patch of the Penrose tiling, and in the limit, you get an example of the Penrose tiling of the plane. So that's one way to think about where it's coming from. Another way that is helpful is illustrated here. So here this is not yet the Penrose tiling, but this is a sort of a way to get a one-dimensional analog of the Penrose tiling, a simpler analog that lives a one-dimensional quasicrystal, by the so-called cut and project method. So what you do is you start with a higher dimensional. We're aiming now to make a one-dimensional quasi-periodic tiling, but we start with a two-dimensional lattice, okay, this square lattice, and then we take a square in the lattice and a cut along some irrationally sloped line. And then as we slide the square along the cut, we get this yellow band. And then every time every time the yellow band contains one of the points in the higher dimensional lattice, we orthogonally project it onto the cut. And if you think about it, you'll then see that if you now look at the points that we've orthogonally projected onto the cut, they come in two possible spacings here. There's a long spacing and a short spacing, and the spacing is always one of those two options. And those spacings appear in a never repeating pattern because the cut is irrational. You know, if it had been rational, we would get some sort of repeating pattern. Okay, and so, but the magic really happens when you do this in higher dimensions with very symmetrical lattice, higher dimensional lattice. And so in particular, the Penrose tiling, you start with, you know, everything is sort of doubled in terms of dimension here. So you start in 4 dimensions with the A4 root lattice, which is one of the most symmetric lattices in 4 dimensions. And then it turns out to have certain special, particularly symmetric, most symmetric 2-dimensional slices through it, but they are irrationally sloped. And you play the same game, but with those 2-dimensional slices. So you basically, you take one of those special 2-dimensional slices, and then again, you take all the lattice points in the A4 lattice near the slice and orthogonally project them onto the 2D slice, and that's the Penrose tiling. Okay, so that's another way to think about it. And the nice thing about this approach is that it helps to understand this kind of very interesting interplay between the symmetries of the higher dimensional lattice, the lower dimensional tiling that you get, and the properties of the tiling under rescaling and the particular irrational numbers that characterize the tiling under rescaling, which is something that I'll get back to, which will be important later in the talk. Okay, and then finally, here are the sort of final 2 ways to think about what the Penrose tiling is. So here I've so again here if you focus on the purple lines are just the Penrose tiling again. They just form these fat and thin rhombi. But now, if you look at each fat rhombus now, you'll see that it's decorated by a particular pattern of thin blue lines. And actually, if you look, you'll see that every fat rhombus is decorated by that exact same pattern of thin blue lines. And similarly, every thin rhombus here is also decorated by some different pattern of thin blue lines. And so yet another way, a fourth way to think about where the Penrose tiling comes from is that you take these 2 tiles, these 2 different rhombi decorated in this particular way, and you say you can stick them next to each other in the tiling only if the blue lines on one tile join up with those on each adjacent tile to form unbroken straight lines. Okay, so you see we get these sort of long unbroken blue straight lines running through the pattern. And we get 5 sets of such lines. This was discovered by Amann. So we get, you know, one set of parallel lines which form a sort of 1-dimensional quasi-crystal pointing along this direction, where you have a sort of short spacing and then a long spacing, short, long, short. It's exactly actually the 1-dimensional tiling we saw on the previous slide. But now you get 5 copies of it because they're overlaid. There's 5 different orientations pointing along the 5 different, you know, vertex directions of the regular pentagon. And so the final way, which I want to mention, because it turns out to be very helpful for finding all of the cousins of the Penrose tiling, is, well, let's call this pattern of thin blue lines, this sort of overlaid pattern of 1-dimensional quasicrystals or quasi-periodic tilings. Let's call that an Amann pattern. And then you can think of the Penrose tiling as being dual to that Amann pattern in a certain sense. So, you know, once I give you the Amann pattern, anyway, let me not get into the details, but there's a kind of natural dualization procedure by which you can go from the pattern of blue lines to the pattern of purple lines shown here, purple tiles. Okay, so far so good. So that ends my sort of brief introduction, whirlwind introduction to the Penrose tiling and different ways to think about where it comes from and what it's about. As I say, it has a lot of special and very interesting properties and tilings like it have a lot of special interesting properties that I'm not going to, well, yeah, I don't think I'll have time to say much about them. So let's get into possible applications. So as I said before, there's really been one famous application so far, which is that they seem to give the best mathematical model for materials, new materials that were discovered in the 80s by this experimentalist crystallographer, Daniel Shechtman, for which he got the Nobel Prize in 2011. And so here you see, this is not his original diffraction pattern, but basically the way they were discovered is, the way crystallographers figure out what crystal they're working with is that they have a little sample of the crystal, and you shine X-rays through you shine a beam of X-rays through the crystal, and then they pass through the crystal, and then they hit a photographic film. And on the photographic film, if you're shining them through a gas or a liquid, you get just a sort of blur. But if you're shining it through a crystal, you get this sort of pattern of highly ordered bright dots. And depending on the pattern of the dots, you can figure out a great deal about what the actual arrangement of atoms is in the crystal, what the shape of the lattice is in governing the crystal. But as I said earlier, there's this famous theorem in crystallography that when you should only have lattices with axes of 2, 3, 4, and 6-fold symmetry. So the funny thing about this pattern is that if you count the number of white dots going around, whoops, did I somehow make my, okay, yeah, if you count the white dots going around, you'll find there's 10 of them. So it appears to be that we're shining along an axis of 10-fold symmetry, and so there was a puzzle of what that's about. And people realized that basically what's going on here is that the atoms are essentially being arranged on the vertices of a Penrose tiling, or a three-dimensional analog of a Penrose tile. So, very good. Now, I want to ask about other possible places where these things could show up in physics. Okay, so that brings me to the first main part of the talk, which is this about this. The basic idea is that, I told you that one of the main ways to think about where quasicrystals come from is that they live in Euclidean space, which itself can be regarded as an irrational cut through a higher dimensional Euclidean lattice. Yeah.
That previous slide, would you know if that's a planar material with a Penrose tiling, or if that's a genuinely 3D fuzzy?
With these materials, you can find that out by taking the material and rotating it. So the actual materials typically have actual icosahedral symmetry, which in 3 dimensions is another of these crystallographically forbidden symmetries. And so you can tell because you can if you rotate it along any of the 5-fold axes of the icosahedron. Yes, there are. Yes. And also nowadays people can make 2D materials, and then with a scanning tunneling microscope actually just image the atoms and see that they form, see what pattern they follow. You can sort of see more directly than you could back then. Okay, so what I want to talk about here is a different way that we've realized that quasicrystals can arise, which is as codimension 1 slices in regular tessellations of hyperbolic space. Okay, so this is a famous, so hyperbolic space is the sort of, by that I mean, the space, here, this is a picture of 2-dimensional hyperbolic space, but later we'll be interested also in 3 dimensions and so on. Spaces of constant, maximally symmetric spaces of constant negative curvature. So this is there's different ways to visualize these spaces in Euclidean space, but this is a famous method of conformally mapping it to a finite disk. And then this is Escher's famous, one of his famous images illustrating what a regular tessellation of hyperbolic space looks like after that conformal mapping. So in other words, you're supposed to imagine that all these different angels and demons are actually really congruent in the original hyperbolic space. But after the conformal mapping, you see that the ones in the center are bigger. And then as we get out towards the boundary, they get smaller and smaller and pile up. Okay. So, for the past 20 years, physicists have suddenly gotten very, high energy physics has been dominated by research on hyperbolic space because of the discovery in 1998 of this phenomenon of holography, or the ADS-CFT correspondence, where it was discovered by Maldacena and Witten and others, and Polyakov, that there was a duality, or apparently a duality, between certain gravitational theories involving a dynamical metric, a dynamical geometry in the interior of a hyperbolic space, and a theory without gravity, but with conformal symmetry, with symmetry under basically rescaling living on the boundary. And then maybe for the past 10 years, there's been a lot of interest in trying to, so that duality as it was originally formulated was a duality between two continuum theories. So two theories involving continuous fields and a continuous space in the bulk and a continuous space in the boundary. But there's a lot of hints that there's something discrete going on. For example, when you calculate the entropy of black holes, they seem to have a finite entropy, in contrast to what you might expect if the theory really was continuous and fields could fluctuate on arbitrarily short scales. What did I say? They have a finite entropy, yes. So the entropy of a black hole has been, found to be the area of its horizon divided by 4 in units of the Planck area, so the so-called Planck length squared. And so I'm just so I'm saying on the one hand there are these various calculations, sort of indirect calculations that suggest that that's the right entropy to assign to a black hole. But on the other hand, if you were just if you really thought the universe was a continuum full of continuous fields that could oscillate on arbitrarily short scales, it would seem that you could fit an infinite number of states into it. Okay, and then so as I say, there were some, but then another thing that's happened recently is that people have been finding it productive to try to rephrase the various aspects, to understand better the various aspects of holography. They've been trying to rephrase it in discrete terms, to put it in the language of quantum computing, quantum information theory, which is normally phrased in more discrete terms, in terms of qubits and gates, etc. And so as a consequence, people have been trying to look for more discrete versions of this holographic duality. And the most famous way that they've been doing that is by, the original way that holography was discovered was all about Maldacena noticing that the isometry group of the hyperbolic space in the bulk here inside the disk is equal to the conformal group of the on the boundary. So somehow this connection between the symmetries of the two theories plays a key role in the fact that the two theories end up being really identified with one another. And so the thought was, it's natural to try to discretize things in a way that preserves, as much of that symmetry as possible. And so people have thought about trying to replace the continuous hyperbolic space in the bulk here by one of these regular tessellations of the bulk, by, for example, tessellating the bulk by just a bunch of heptagons, 3 of which that meet at every vertex, for example. And in that way, you get a space which you get a geometric object which doesn't have all of the symmetry of the original hyperbolic space, but has a gigantic infinite subgroup of it, exact subgroup of that original symmetry. And to make a long story short, maybe to foreshadow before I move on to the next slide, to make a long story short, what we had pointed out in this paper here was that in the two-dimensional case, like in the picture we're looking at here, that if you take those hyperbolic tessellations of hyperbolic space, and you imagine sort of cutting them in larger and larger rings, that in the limit, that you get a pattern around the ring that in the limit, as you go out to the boundary, becomes a quasicrystal. Okay, becomes an aperiodic tiling, very similar to the one-dimensional Fibonacci lattice that we saw on the one-dimensional Fibonacci quasicrystal that we saw on that earlier slide. And in this more recent work with Justin Culp, we have shown how that works in one particular case, for the first time in one dimension higher, where the bulk is three-dimensional and the boundary is two-dimensional. But anyway, it turns out the story is a lot more interesting there, and as I'll get to and explain in a moment. But so first, I want to explain, the reason that I find that interesting is that, on the boundary here, you're supposed to have a theory where the key symmetry that it has is conformal symmetry. The theory is supposed to be invariant under rescaling everything, rescaling lengths. And that sort of theory shows up in physics in a lot of different places. In particular, any physical system, if you tune it right to its critical point, right at the point of right where it's about to make it's a second order phase transition between two phases, it always becomes one of these conformal theories. And a puzzle is what is the natural way, if you wanted to sort of discretize such a theory, so that, for example, you could both for analytic but also for numerical reasons, if you wanted to try to simulate the physics of that system on a computer, you might want to be able to discretize it. And normally for a system where translational symmetry is the key symmetry of the theory, typically you will discretize such a system on a lattice, because it usually makes life, anything you want to do, either analytic or numerical, simpler. That you discretize it so it can fit on a computer, let's say, but you at least manage to keep an exact discrete subgroup of the original symmetry that was playing an important role in the system. And the question is there a way to do something analogous for conformal theories where conformal symmetry is the key symmetry? And what I want to say is that there are reasons to think, although we don't quite have, although I haven't yet, well, I have some sort of incomplete thoughts about how to do it, but I think the right way to do it is not on an ordinary lattice, but on one of these quasi-periodic, special quasi-periodic lattices like the Penrose tiling, because there is a sense in which these quasi-periodic lattices retain, they keep an exact discrete subgroup of the scale invariance in a way that's very analogous to how an ordinary lattice keeps an exact discrete subgroup of the translational symmetry. And so in that sense, this fact that when you discretize hyperbolic tessellations in the bulk, that when you split them into shells, that they become quasicrystals at the boundary where conformal invariance is supposed to be important, is a bit of evidence for this, and so we'd like to understand that better. Okay, so to describe some of the easiest way to see why a lattice sort of why a quasicrystal or a quasi-periodic tiling like the Penrose tiling does a better job than an ordinary lattice of retaining of comporting with scale invariance is I think this one. So here I've made, yeah.
I'm not sure the sense in which you use scale invariance. So there's a local sense, like the captures conformal invariance, or is it just overall?
So I normally one is It's actually a very interesting question, is whether the argument that I'm about to make. Normally when in this ADS CFT correspondence, when people say that there's a theory with conformal symmetry on the boundary, what they mean is the conformal group as the finite dimensional extension of the Poincare group. So it's just, you know, the ordinary symmetries of Minkowski space or Euclidean space plus overall global scale transformations, and then a few more so-called special conformal transformations. But somehow the key one, which I want to illustrate in this point, is and which seems physically like the key one, is that these theories are globally symmetric, undertaking the whole space and globally stretching it. Well, I don't know how to. I haven't understood that part of the story yet. How exactly those would act on. So yeah, so I haven't really thought carefully about the special conformal transformations. Yeah. And then, oh, sorry, just to finish the answer to that question. Now, as a matter of fact, I do think there's a kind of, I think that the statement is there's a kind of there's some sort of analogous statement that's even true for local conformal symmetry, which has to do with different ways you can, you know, when I was describing the story a moment ago, I said, you know, I made it look as if I was going to take spherical shells in particular and look at those as you go further and further out. And then, you know, when you do that, jumping from each shell to the next one is indeed a global rescaling, just a global rescaling of the shell. But actually, you know, there's a kind of analogous story where you can start with a seed of any shape and then grow it layer by layer, and in that sense get some analogous result for any a more local conformal transformation. So I think there is an analogous story, but I haven't really understood it yet. But maybe before I go further, I should tell you what I even mean, or explain to the rest of the audience. So you know, so anyway, so this diagram is just supposed to show, here I have 3 layers of a square tiling. So, you know, I start with the big blue square tiling, and then I could, there's a kind of local rule that I could use to construct more and more refined square tilings, of course, which is I can just, you know, plunk down construction workers on each of the tiles and tell them, you know, just go and split your tile into 4 smaller tiles in the natural, 4 smaller squares in the natural way. And when you do that, you know, you get the more refined pink square tiling here. And then you can, of course, continue that and, you know, go ahead and split each of those new tiles into 4 smaller tiles, and you get this even more refined black tiling at the bottom. So yeah, it looks like the blue tiling in that sense locally contains all the information you need to construct the black tiling, the more refined black tiling. You know, but if you try to go in the opposite direction, then you run into trouble. The black tiling does not have the local information needed to reconstruct the coarser blue tiling. So if I now plunk down, you know, 4 different construction workers in different spots on the tiling and tell them to start grouping 4 tiles together to make bigger tiles and then even bigger tiles, you know, there's 4 incompatible choices they can make about how to get going. And so the pink guy over here might start constructing his bigger tiles like this, but the orange guy would make a different choice over here. And, you know, eventually when they grow their tilings large enough, they're gonna run into conflict with one another, and there's gonna be a defect between them. Or stated another way, you know, if I start with the black refined tiling, you know, there's just multiple different more coarse tilings that are all equivalently good coarsenings of it. So, you know, here the blue and the purple tiles, blue and purple tiles are 2 different tilings that are both two coarsenings up. And, you know, there's 16 options now, 16 different options. And if I went one further layer, there would be 64 different options. So somehow the black tiling does not retain its translational invariance intrinsically makes it impossible for it to know about what coarser tiling it started from. Okay, and that's a very important difference that makes it very different from the Penrose tiling. So here, what I've drawn, so here's another picture of the Penrose tiling. So again, the purple lines, if you focus on them, that's the Penrose tiling. But now here I've also drawn, you know, on each fat tile, I've split it into smaller pink tiles according to a certain pattern, and every fat tile has been split up in the same way. And similarly, every thin tile has been split up in a different way, so that underneath, so it's, you know, it's analogous to what I did on the previous slide where I took every square and divided it into 4 smaller squares. But now I take every purple tile and split it into these smaller pink tiles, and what I get is a new tiling which is locally indistinguishable from the Penrose tiling. If I plunk you, apart from the fact that it's rescaled by the golden ratio, if I plunk you down in the pink tile or the blue tile, in either the purple tiling or the pink tiling, and give you the rest of your life to explore and make measurements, you'll never figure out which tiling you're in, because there's no and any patch, no matter how large, that appears in the purple tile also appears in the pink tiling and at the same frequency. So they're locally indistinguishable in that sense, even though globally they're in general distinct and can't be. There's no way to exactly line them up with one another even after you rescale them. But the difference now is that, so not only is there a local rule for taking every purple tile and splitting it into smaller pink tiles to make an equivalent tiling, now, you know, there's also just a local unambiguous rule for taking the pink tiles and gluing them together to get the larger purple tiles from which they came. So there's a sense in which, just like with the square tiling, there's really an infinite hierarchy of, you know, coarse tilings and finer and more refined tilings with smaller tiles that are all locally equivalent to one another. But in some sense, any layer in that hierarchy knows everything about all of the tilings that lived above and below it. Yes. Yes, it's unfortunately because of the way the purple tiling is covering the pink tiling, it's a little hard to see what the pink tiling looks like. But if you remove the purple lines, the pink tiling looks exactly like the purple tiling. It's just smaller. So here's an example of one of the fat rhombuses in the pink tiling, and here's an example of one of the thin rhombuses in the pink tiling. And it's confusing because the decimation rule, the tiles get cut in half by the purple tiles.
Sorry, can I also ask? So you're saying there's a unique way going in the hierarchy, or there is one unique hierarchy for each? Is that, am I understanding this?
Okay, there's various confusing points, and I'm not 100% sure which one you're asking about, but let me answer 2 questions, because probably anyway, someone will be confused about this. So the first thing to say is that there is not one Penrose tiling, there is an infinite number of Penrose tilings built from these same tiles according to the same rules, and they're all locally indistinguishable from one another in the sense that if I plunk you down in one of them, you can explore for the rest of your life and you'll never figure out which one I put you down in, because any finite patch, no matter how large, that appears in any one of those Penrose tilings also occurs equally often in every one of the other Penrose tilings. So, however, they're globally distinct in the sense that if I give you 2 of those tilings and you try to actually overlay them in a way where they agree everywhere in the plane, it'll be impossible. There's just no way to line them up so that they overlap each other over the entire plane. Now, so suppose we take one such tiling, the purple tiling here, then what I'm saying is now using these local rules, I can construct from it a whole infinite hierarchy of tilings with smaller and smaller tiles, but ultimately after rescaling just other equivalent Penrose tiles. But same goes in the other direction. The local rule is completely invertible. So there's also a local rule for grouping tiles together to make bigger tiles. So I get this sort of infinite tower of tilings that are all related to each other by so-called inflation or deflation operations. Exactly. Whereas with any periodic tiling, oops, sorry, I got logged out of my iPad here. With any periodic tiling, that can never be the case. It's fundamentally in conflict with the translational symmetry of the tiling, that a more refined tiling can't know. There's no local rule, but there's no local information in the more refined tiling that tells it about which coarser tiling it comes from. But somehow with these aperiodic tilings, they do know. They keep, this is one of the ways, it's the way that I find the sort of simplest to explain that they know about discrete scale invariance in a way that periodic tilings don't. They preserve discrete scale invariance in a way that periodic tilings don't. There's various ways to see that, but did that answer your question, Pavel?
Yeah, so if I have the purple one, I will always know what the pink one is.
You can unambiguously derive the pink from the purple, but you can also unambiguously derive the purple from the pink.
Okay.
And to go in either direction, you don't need any global information. So I imagine the process of gluing or splitting being done by local construction workers. They don't need to coordinate with one another at different places in order to get the answer. They can just look at the local tiles in their neighborhood and figure out who lives, the local pink tiles tell them what the local purple tiles are, or vice versa. Exactly. That's what I'm saying. There's a local, and in the periodic case, there was a local rule for decimating tiles, for breaking them up and creating a smaller equivalent tiling, but it was not invertible. There was no unique inverse of that, local inverse of that process. Whereas with the Penrose tiling, there is. It's both local and invertible, this rule. You can go arbitrarily far down and then come arbitrarily far back up and get back to the same tile without any memory, having to remember where you started from. Does that make sense?
Good. Yeah.
Okay. Okay, so sorry. So I realize I'm going a little slower than I had planned. So let me just recalibrate here. Okay, so let me just be quick about this. So how do Penrose tilings now appear in hyperbolic space? So here's a tiling in hyperbolic space. Okay, so again, this is like Escher's angels and demons. Really, this is a tiling where every tile is a heptagon, and three heptagons meet at each vertex, like this one. And that's a sort of putting three heptagons together. Of course, you wouldn't be able to do that in flat space, but it's no problem in hyperbolic space. Okay, so what's going on here? So suppose I start with a finite seed of tiles here, the dark gray patch. Then there's various ways to label the boundary, but I find it easiest to describe this one. So I draw a circle around the boundary here, enclosing my initial patch, and then it cuts through these tiles right outside the boundary of the gray patch. It cuts them in half, and let me label each of those tiles by the number of, sort of making a mess here. Let me label, so here I've labeled this tile a 3 because if you look, there's 3 edges that lie inside the cut. There's sort of a 2 plus 1/2 plus 1/2. Whereas here I call this a 2 because it has only 1/2 plus 1 plus 1/2, or 2 edges inside the cut. Okay, so by that rule, I'll label all the tiles around the boundary. Okay, so here I get 2, 2, 3, 2, 2, 2. I got it. This one has 4. Inside the boundary. Fine. So that's going to be my labeling scheme. I'm going to have some string of numbers with which I've labeled the geometry of the boundary. And then, now suppose I start with initial seed here, and then I grow it. I add 1 layer of tiles around it. Well, so using that same scheme as before, I can label the boundary of the original seed, but then I can also label the boundary of the new larger seed that I grew by adding one more layer of tiles. And what you find is that the labeling around the initial scheme, the string here, is related to the string on the larger seed just by a simple local substitution rule. Every time I had a 2 around the boundary over here, I replace it by the pattern 2, 2, 3 on this larger boundary. And every time I had a 3 on the boundary over here, every time I had a green tile like this, I replaced that 3 by the string 2, 3 over here on this boundary. And so there's a local substitution rule, very analogous to the substitution rule that we just mentioned before that generates the Penrose tiling, but a one-dimensional analog of that. And that substitution rule you can show generates in one of these aperiodic tilings, like the one-dimensional Fibonacci, very, very close to the one-dimensional Fibonacci quasi-periodic tiling that we saw earlier in the talk. Okay, so that's how it works. It's all very simple in the case where you're looking in two-dimensional hyperbolic space. Two-dimensional hyperbolic space, if you take any of these regular tessellations, you know, where a bunch of octagons meet 4 at every vertex, any tessellation you want, for any P and Q that you want, you get a corresponding quasicrystal in this way, aperiodic tiling as you head out to the boundary. So now, we wanted to understand something, the corresponding story in higher dimensional hyperbolic space. In higher dimensional hyperbolic space, there's only a handful of tilings. They were all found by, well, the list was completed by Coxeter, who, as you probably know, well, there's memorials to him out there in the lobby, and he was a great member of the U of T math department for decades and decades. So here is the most beautiful hyperbolic tiling of three-dimensional hyperbolic space. So this is the self-dual tiling. This is sort of, you know, an attempt to depict the self-dual tiling of hyperbolic space by icosahedra. So now every tile is an icosahedron, and 12 icosahedra meet at every vertex. Okay, and we'd like to do something analogous where we start with a sort of initial seed, and then we somehow label the boundary of that seed, and then grow that seed by one more layer of tiles and relabel the boundary of that new larger seed, and then grow it by one more layer of tiles, relabel the boundary. And what I want to explain is that once again, if you think about it the right way, you again generate an aperiodic tiling. There's actually just a few tiles that label the boundary, and a local rule, one of these local invertible rules, like in the Penrose tiling, for either growing the larger tilings or reversing the process and recovering the smaller tilings from which they came from. And in fact, in my original 2020 paper, I had hypothesized, I had conjectured that would be the actual Penrose tiling, the honest to God Penrose tiling that you would grow in that way. And then my student Justin, who's collaborating on this with me, was speaking to Penrose, was visiting PI a few years ago, and Justin mentioned this to him, and it turned out that he got very excited and said, "Oh, you know, I was at the IAS in the 1970s, and Thurston, I remember this conversation. Thurston said the same thing, except he said you had to, you know, cut along horospheres." And anyway, so he had to not get into the details because I'm running out of time. You know, basically he had the same conjecture that somehow if you slice up this tiling, that you get Penrose tiles. Now, in short, that's almost right, but then it turns out to not quite be right. You get some new tiling, which is a hell of a lot like the Penrose tiling, but not quite the Penrose tiling. It's some apparently interesting new tiling that only can live in hyperbolic space and can't really be easily mapped to flat space. So to briefly say how it goes, so again, I asked DALL-E here, I asked for a geometric to try to give some visualization. So suppose I have a bit of the seed of the tiling here, and I want to look at the sort of surface of that seed. Well, it's a bunch of icosahedra that have been glued together, and all their faces are all ultimately congruent triangles. So it's a sort of surface, it's a bumpy surface of these triangles, which are the faces of the icosahedra in the seed. So I asked it for a bumpy geometric surface made of triangles. It gave me this. I thought this one I thought it did rather well on. And so in brief, if you look at the edges where triangles meet, they come in only two varieties. Basically, there's an edge that bumps out, which I've labeled with a solid pink line here, and then there's an edge which, a valley, which pokes into the surface, which I've labeled with the dashed lines here. And so in that language, this is now not DALL-E, this is an actual depiction of a portion of the surface of such a seed. So the black curves here, the black solid and dashed curves show the surface of a portion of the seed at one layer. And then I've added one more layer of tiles of icosahedra to that seed to grow a bigger seed. And now the new surface is represented by the red curves here. Okay, and it looks like a huge mess. And it's even worse because I've had to distort it horribly to depict it on the two-dimensional plane. But at the end of the day, it turns out there's a very neat, simple story, which is that there's really only three types of vertices that appear on the original surface. There's a vertex where the pattern of edges that bend out and edges that bend in look like this, or like this, or like this. And then over each such vertex, the new higher surface, which I had drawn with the red curves, red lines on the previous slide, although here I've drawn them with green curves, the new higher surface above each of those vertices is shown in this corresponding figure. And using this approach, using this sort of just thinking about it one vertex at a time, you can show that the substitution rule that takes you from one layer to the next layer, the substitution matrix here, it turns out to be exactly like the substitution, it's exactly the same as the substitution matrix for the Penrose tiling. So we thought for sure, okay, this is a tiling that has points of five-fold symmetry. It's a two-dimensional tiling with points of five-fold symmetry. Same substitution matrix as the Penrose tiling. It's got to be the Penrose tiling. But to make a long story short, we then found a proof that it's not the Penrose tiling. After sort of trying unsuccessfully to find a map from this to the Penrose tiling, we found a simple argument that it can't be equivalent to it, which I don't have time to get into. So it's just, so the two takeaway points that I want to get from this first part of the talk, and then I think I unfortunately just will not have, sorry, where am I in terms of time? 2 minutes, yeah, that's what it is. So unfortunately, I'm going to have to jettison the second half of the talk. I'm happy to tell anyone, but I apologize for that. So let me just end this first part by taking the takeaway point that a new phenomenon that happens in three-dimensional hyperbolic space and higher, which we didn't see when we were just looking at two-dimensional hyperbolic space, is that there appear to be it appears to be that you can split a regular tessellation of hyperbolic space into foliations. In this case, these are these triangulated surfaces that form an infinite stack, just like the stack of Penrose tiles. They are quasi-periodic tilings, just like the Penrose tiling, that come from an invertible local substitution rule, just like the Penrose tiling, so that any given slice knows everything about the whole infinite stack of leaves and the foliation that lie above and below it. They're new tilings that we did not expect, and that appear to not be, they can't live in flat space, even though we were sort of expecting that these leaves would essentially be kind of ripply versions of the flat slice of the flat foliation of hyperbolic space. So we're to be honest, we don't understand very well their actual shape, but they're these new, beautiful new tilings. And it connects to this idea of holography that I was mentioning at the beginning, in the sense that the traditional view, physicists' view of holography, is that you have these two geometric spaces, the hyperbolic space and its boundary, but the duality is, the sort of holography is really at the level of the two physical theories, the field theories that live, one field theory or supergravity theory that lives in the bulk, and one conformal field theory that lives on the boundary. But here we see that there's this sort of in a sense, holographic phenomenon that's already occurring at the level of just the discretized geometry. This fact that the natural discrete tessellations of the space that preserve a large discrete subgroup of its symmetry group, they have these natural foliations into these tilings where one leaf in the tiling already knows everything about the space of one dimension higher in which it's embedded. So, and it sort of knows everything in a way that's just locally encoded, which is, as I emphasize, really a different than what happens with tilings in flat space, or in flat space in general. Okay, so I apologize. I also apologize to Sotirios, who I know is here, for not getting to part 2 of the talk. I completely blew it with time management here. But anyway, let me jump to the end and say that. Well, maybe I'll just end there. Thank you very much for listening, and yeah, I'll hope to tell you about the other things some other time.
Okay, so we are a bit over time. Maybe one question, and then maybe you can tell us more over coffee. Eric?
So is there some, too well familiar, I suppose, with people who do this in R3, because Bob Moody was a former colleague, but so is there any sort of similar theory in hyperbolic space where tilings and aperiodic tilings and so forth?
So that's the thing. Not that I know of, and to my understanding, I believe it is the case. What we say in that paper, and I've been. It's a little bit surprising to me that it wasn't noticed before, but I think that paper of ours was the first to point out that you get these quasicrystals when you divide up. You sort of naturally get quasicrystals from dividing up hyperbolic space. And then now this one that we're working on, I think, is the first indication that you get new ones that are sort of you wouldn't have seen in flat space. It's not just a new way to get the same old flat space tilings. So yeah, no, I think it's very early. I mean, I just think certainly we don't understand. So there's a lot that I don't understand, let alone a complete theory of how they're.
Have Moody or his students taken any notice yet, or any of the people from the traditional?
That's a good question. I'll definitely send it to him or them when we're done with this paper. I think in the previous paper, I thought we were not discovering anything new quasicrystal wise. I think I thought that the interest had to do with sort of the relation with this discretizing holography program. Whereas now I think this is a more, some new interesting, also just purely mathematical objects. So I'll definitely send it to them. But I haven't yet.
Okay. Gosh, maybe I should also offer one question to the people online, if anyone online wants to ask a question. And if not, we can just.
Oh yeah.
We can thank the speaker and adjourn to coffee, and this next talk will be at 3:30.
Okay, thank you. Oh yeah, thanks so much for the invitation.